We are jumping right into a big one today, PointWorld, a large pre-trained 3D world model. And the mission here is, well, it's profoundly ambitious. They're trying to create a single general-purpose model that predicts physics. So how the world moves based only on what a robot sees and what it plans to do.
And they really boil it down to three huge takeaways. The first is what they call unification. PointWorld represents the entire scene, the state, and the robot's action completely within 3D point flows.
So it's just points in, points out.
Exactly. You feed it scene points and robot points, and it just predicts how the scene points are going to move. It really simplifies the problem.
Okay, second big headline, scale and performance. They train this on what they're saying is the largest 3D interaction data set out there. We're talking 2 million trajectories, about 500 hours of data.
And they're open sourcing it, which is fantastic. But the key is that the model is fast, like 0.1 second inference latency.
Which means you can actually use it for real-time planning.
Right, which leads straight to the third headline, zero-shot generalization. A single pre-trained model with no extra tuning can get a real Franca robot to do this huge range of tasks.
Like what kind of tasks are we talking about?
Rigid pushing, sure, but also manipulating deformable objects, opening drawers, even using tools, all from a single camera input. It's wild.
That kind of generality is, that's the holy grail for robotics.
Okay, let's unpack the core philosophy, because this isn't just another visual model. When you're building a world model for a robot, you need to forecast really complex stuff.
Exactly. You need to know about contact and articulation, stability, deformation.
All things that are fundamentally 3D.
They're all physical, spatial problems. And, a lot of prior work used 2D generative models that might look okay, but they lack physical consistency.
Or you have physics simulators that just have a brutal sim-to-real gap.
Right. So PointWorld just grounds everything in 3D physical space from the start. They use point clouds from RGB-D cameras to represent the whole scene. So by using a point cloud, they're emphasizing the geometry and the physical interaction over, say, just a photorealistic appearance. What's the benefit there?
A few things. One, it's accessible. You can get a point cloud from a real, partially observed scene. And two, and this is maybe the more interesting part for an ML engineer, you don't need object priors, no segmentation, no material properties.
You're just predicting spatial displacement.
Yep. Which means you can use a simple, stable L2 loss on the point movements. It forces the model to focus on the fine-grained contact dynamics right away.
That's a really smart simplification, trading that visual fidelity for a solid physical grounding. But let's talk about what I think is the most ingenious part, the action representation. They represent the robot's intended action, not as joint angles or something, but also as 3D point flows.
Yes. They derive them right from the robot's own geometry, its URDF, using forward kinematics. They literally treat the robot itself as another moving point cloud.
So the model sees the scene points, it sees the robot's future point trajectory, and it predicts how the scene will react.
That's the whole task.
And that makes the action fully observable. If I just used a 6-dove pose for the gripper, I'd miss it if the robot's elbow bumped into something.
You'd miss it completely, especially if it was occluded. But by using the robot's geometry as an action, you always know which parts of the robot are interacting with the world.
That must be why they call it embodiment agnostic.
Exactly. The representation works for a single-arm Franca or a big bimanual humanoid because you're just modeling the geometry of the physical interaction itself.
That said, they didn't use the entire robot's geometry, which would be a ton of points. What did they find in their ablations?
They found a sweet spot. For efficiency, they sampled points only from the grippers. Just 300 to 500 points per gripper.
And that was enough.
It was not only enough, it actually outperformed using dense, full robot point flows. It's that Goldilocks zone. You get the crucial geometric info for contact, but without all the computational overhead.
So the final task is, initial scene points plus a sequence of gripper points equals the predicted movement of the scene over the next second. Let's get into the recipe that makes this thing scale. They use a multi-step or chunked prediction, not the usual one-step-at-a-time autoregressive approach.
Precisely. They predict the whole future sequence, all 10 steps, in a single forward pass.
Which is so different from a recurrent model that predicts a step, feeds it back, predicts the next.
Right. And that chunked prediction is crucial for robotics for two reasons. First is temporal consistency. You predict the whole sequence at once, you get smoother, more believable dynamics.
And second is the computation, right, for planning.
Yes. the amortization of computation. If you're using a planner like MPPI, you need to simulate thousands of possible futures very, very quickly. Chunk prediction makes that feasible.
Okay, architecture choice. They went big. They chose Point Transformer v3, PTv3, as the backbone for the ML folks listening. Why PTv3?
It really just comes down to scalability. PTv3 is designed to scale up to 1 billion parameters while keeping memory and runtime manageable. They needed something that could grow with their huge dataset.
And the feature engineering was pretty clever. They didn't just use the 3D points. They injected an objectness prior from a frozen 2D model.
Yeah, from Dino v3. And the way they did it was so simple. They just projected the 3D points back into the 2D camera views and grabbed the corresponding visual features.
So you get all this rich, pre-trained context about object boundaries and semantics without having to do any explicit 3D segmentation.
Exactly. It gave them a huge accuracy boost. It just shows how powerful leveraging these 2D foundation models still is for bootstrapping 3D understanding.
Makes sense. It's a very efficient way to get semantic priors into a geometry-first model. Now, let's talk about the loss function, because that's often where the real magic happens with messy real-world data. They had two big challenges.
The first one is a classic. A really sparse training signal. In any given scene, only 1 to 5% of the points are actually moving.
Right. So if you use a standard L2 loss, the model just learns to predict static for everything and gets 95% accuracy without learning any physics.
It learns a ton about the background, which is useless, so they had to teach it to focus.
How do they do that?
They used a weighted regression objective. Each point's contribution to the loss is reweighted by how much it actually moved in the ground truth. It just forces the model's attention and gradients onto the moving, interacting parts of the scene, the parts that actually matter.
A dynamic attention mechanism inside the loss. Super smart.
Yeah.
What was the second challenge?
Real-world noise. RGB-D sensors, tracking systems. The data is never perfect. If you overfit to that noise, your model won't generalize.
So they needed some kind of regularization?
They used aleatoric uncertainty regularization. So instead of just predicting the displacement for a point, the model also predicts a variance. It predicts how certain it is about its own prediction.
I see. So it can essentially learn to downweight the loss on points it thinks are noisy.
Exactly, and they paired that with a Huber loss, which is more robust to outliers. And what's really interesting is that this uncertainty seems to capture not just sensor noise, but physical uncertainty. Like it's higher along the edges of a piece of cloth, where the motion is just inherently less predictable.
Let's shift to the foundation of all this, the data. 2 million trajectories, that number is staggering. But with real-world data, quality is everything.
That's the understatement of the year. The raw DROID data was not good. The depth was inaccurate. The camera poses were off. They couldn't just use it.
So they had to build a whole annotation pipeline just to clean it up?
A huge 3-stage markerless pipeline, stage 1. They just threw out the sensor's depth and replaced it with higher quality depth estimated from stereo cameras using foundation stereo.
Okay, so that fixes the depth. Stage 2 was the camera pose.
Correct. If your camera pose is off by a few centimeters, your whole 3D world is wrong.
Yeah.
They used this custom optimization that aligned a rendered model of the robot with the observed depth.
And that worked.
It worked incredibly well. They got the median errors down to 1.8 centimeters and 1.9 degrees. That is a massive amount of effort.
And the final stage was actually getting the ground truth 3D motion.
That's the occlusion-aware tracking. They use a 2D point tracker, lifted those tracks to 3D with their new refined data, and, this is the breakthrough, they propagated visibility flags.
So they could filter out points that were occluded during training.
Exactly. No supervision on points you can't see. This whole pipeline is what let them recover clean 3D flows for over 60% of the DROID data, creating a data set you could actually learn from.
So let's look at the results. We know the gripper-only point flows won out for the action representation. Why did the other methods fail? Low-dimensional actions are pretty standard.
Yeah, and they just lagged significantly. Things like a 6-DOFA pose or joint positions, they just don't have enough geometric detail to predict precise contact dynamics.
But why did the dense full robot point flow underperform the gripper-only one? You'd think more information would be better.
The hypothesis is it's a signal-to-noise problem. In the real world, which is noisy, modeling every inactive part of the robot just adds noise and dilutes the learning signal.
So the gripper-only version focuses the model's attention right where the action is.
It's a high concentration of the relevant information. And the experiments also confirm something huge we see in LLMs and vision models: scaling laws. They saw this really clean, predictable log linear relationship. As they increased model size and data, the prediction error went down smoothly.
And that is a major scientific result. It suggests 3D world modeling isn't some black art. It's an engineering problem with a clear roadmap. More clean data and bigger models lead to better physics prediction.
Which brings us to the ultimate test, generalization. How did it do against specialist models?
The zero-shot performance is what this is all about.
It was incredibly effective. The model trained on both real and sim data was deployed in a totally new, unseen lab. And its performance was comparable to models trained from scratch just on that lab's data.
Wow, so you get specialist performance for free, zero shot.
And if you do fine-tune it, it blows past the specialists immediately. With 20 times fewer updates, it completely closes that sim-to-real gap. It just proves that combining sim and real data gives you the strongest foundation.
They also looked at partial observability, right?
Yeah.
Which is a huge issue in the real world.
Yeah, they trained models where they randomized the number of cameras available during training.
And that helped.
It paid off big time. Those models were the most robust, whether they were tested with 1, 2, or 3 cameras. It suggests the model learned a stronger internal representation of the world, so it could infer what was happening even when parts were occluded.
Okay, let's get to the payoff. Real-world deployment. They took their single pre-trained checkpoint, hooked it up to an MPPI planner,
And put it on a Franca robot with a Finray gripper that the model had never even seen before.
So it had to generalize to the environment and the tool. And what could it do?
The whole range. It did simple rigid pushing, like moving a box, but then it did much harder deformable manipulation, like folding a scarf or placing a pillow.
Folding a scarf zero shot is notoriously difficult.
It handled articulated objects, too. Opened a microwave, which is a revolute joint, closed a drawer, a prismatic joint. It even showed it could use tools, like sweeping with a duster.
That diversity is the real proof that it's learning general physics, not just memorizing tasks.
Absolutely. And they noted something interesting about the training mix.
The sim versus real question.
Exactly. Models trained only on real data were too conservative, kind of scared to interact with things. Models trained only on sim data would get confused by cluttered real scenes.
But the mix of real and sim.
That was the sweet spot. It gave them the most balanced, effective behavior in practice.
So to sum this all up, PointWorld is a really significant step. They unified state and action into 3D point flows. They proved at scales, built this incredible data set, and demonstrated really impressive zero-shot generalization on a physical robot.
It shows us that building these large-scale foundation models for physics is not only possible, but it follows the same kind of scaling laws we're used to. But there's one critical limitation in how it's currently formulated that really points to the future of this research.
And that's the kinematic assumption, right?
Exactly. Right now, PointWorld assumes the robot is a perfect kinematic executor. It models what will the world do if the robot perfectly follows this path.
It doesn't model the robot's own dynamics.
It doesn't. So the provocative thought to leave you with is this. How does this field evolve when the models have to jointly reason about the robot's own dynamic limits? Things like actuator torque, compliance, tracking errors from contact.
What if the scene isn't static to begin with? What if other things are already moving?
That is the next frontier, moving from learned kinematics to truly comprehensive causal dynamic physics. That's where the next big breakthroughs are going to be.